I have a PowerPoint here. I'm going to go through the PowerPoint, and hopefully this will clarify how the assignment is actually drawn. So let me see if I can minimize this a bit, because you don't need to see what the next slide is doing. So contours. Basically, this is an image of the augmented reality sandbox, which is what we would be using if we were in person to talk about contours, but because we're not in person, we are not using it. So contours, they really is a contour line is connecting a moment of equal elevation. Okay, so if you look at this diagram here, let me grab my little pointer. Look at the diagram here. When we look at the topographic map, it's flat, right? You can't really tell what these lines are, but if you explode it into a 3D view, you can see that the 20 contour line is running basically along this 20-foot elevation change, okay? Contours can never cross each other. They can stack on top of each other, but they can never cross each other. So a contour line is equal elevation. They always connect. So contours have been used by surveyors and engineers to display relief in all design projects and aspects of design projects. So contours are used for highway projects to figure out volumes of things, and also to make sure we're placing so water's draining off site in the proper way. Contours are drawn on maps by interpolating between points whose position and elevation have been measured and plotted. And you're going to see that with the assignment, okay, because you're going to be interpolating a ton on that assignment. The vertical distance between consecutive level surfaces forming contours on a map is called a contour interval. So if our contour interval is 1 foot, it means that contours are displayed every 1 foot. If the contour interval is 5 feet, contours are displayed every 5 feet. In the assignment, you're going to show the contour interval as a foot. Common intervals on larger scale maps used in engineering design are 1 foot, 2 foot, 5 foot, or 10 foot. Contour intervals selected depends on the map's purpose and scale and the diversity of the relief area. So, case in point here, a lot of the topographic maps that are shown for like out in the Rocky Mountains are actually 100-foot contour interval because the elevation changes so much. If you looked at the elevation map, the lines would look like they were right on top of each other, so you wouldn't really see an elevation change. It'd be just too cluttered if you did it at like a 1 foot interval. The page would just be black because of the elevation relief that's there. But if we're working in an area that's relatively flat, like a farm field or something like that, we might have 1 foot contours or even half-foot contours just to see how much elevation change there is across that site, okay, and where water's draining and things like that. So relief of contours, or contours shown in relief, can change depending on the site itself. All right, so spot elevations are used on maps to mark unique or critical features. Okay, so we have potholes or dips in terrain, or even mountain peaks, valleys. So it would basically points, or those spot elevations are used for like a high point or something like that, or a low point. Computerized mapping and contouring systems are replaced, or have replaced, manual plotting methods, and you're going to see why with the assignment. You guys are manually going to be plotting. It's painful, but it helps give you respect for what contouring actually is. And you'll see how easy it is once you get it into the computer or CAD system. All right, so contour lines must close on themselves, either on or off of the map. They cannot dead end. Okay, so contours never stop. They travel forever. unless they run into themselves. Then they'll stop. So a point where that might happen is if you're going up a hill. That moment of elevation, say it's 100 feet of elevation, is always going to end on itself. Okay, they never terminate into another elevation. They never terminate because Earth is a sphere. They just never just end. Contours are perpendicular to the direction of maximum slope. So if you look at this map here that I have, these flow arrows are showing that water is flowing perpendicular to the contour itself. Okay, so if you look at a contour, you're always going to know which way water is flowing based on the direction of that contour. So it's always, water always flows perpendicular to the contour. Distance between contours indicates the steepness of the slope. So the wider apart the contours are, the more gentle slope. The closer they are together, the more steep slope. So as you can imagine, out in the Rocky Mountains, the slope is very, very steep in some of the mountain areas. So you get contours that are smashed right together, even on top of each other. Where if you're in farmers' fields, like around here, they are spread a lot further apart because the elevation relief does not change drastically. And then if there's even or parallel spacing, it means that it's a pretty uniform slope. So if you look on the diagram here, these contours right here are pretty evenly spaced apart. So it means the slope is pretty much similar in this area. But when you get up in here, it's a less of a slope up in here than it is here. This is more steep because the contours are closer and uniform, and this up here is less of a slope because they're wider apart and they're pretty similar in change. All right, so to beat a dead horse on steep or gentle slopes, here's diagrams right here. So irregular contours normally suggest that it's pretty rugged terrain. Smooth would imply that it is a uniform rolling terrain. Okay. Concentric closed contours that increase in elevation represent hills. Concentric closed contours that decrease in elevation represent holes or potholes or ponds. Okay, so you can sort of see that in this diagram here, where there's like a caldera from a volcano, say, and they're decreasing in elevation from 300 down to 290. That makes a hole. Okay. So contours forming a closed loop around lower ground is called the depression contour. Spot elevations inside the lowest contour and they point to a bottom of a hole. Okay, so a lot of times you won't have point elevations in there or an actual spot elevation, especially if it is a depression, because a lot of times they couldn't get elevation in there because it's full of water or volcanic activity or something like that. Then contours of different elevations never meet except on vertical surfaces such as walls or cliffs. That's where they're just stacked on top of each other. So they never ever meet. It's just they look like they do because they're stacked on top of each other. All right, characteristics of contour. Contour cannot branch into two contours of the same elevation. That doesn't happen. Contour lines cross a stream point upstream and they form V's. Okay, so where they cross a stream, upstream forms a V. So if you're looking at a stream, the elevations increase as you move up the stream. Downstream, the way the water's flowing is going to decrease in elevations. So those V's always point to a higher elevation in the stream. And then ones that go down ridges will form U's, and they'll cross that ridge crest. Okay, so when they form U's, it means that you're moving up in elevation as well. And contour lines that go in pairs up valleys or along sides of ridge tops. Okay, so they actually will go in pairs along those valleys or ridge tops. All right, so we use contours a lot to tell us what cuts and fills and volumes are on a road project. So this is a road topographical map of a road cross section or a road area. And so you can see in this area right here, obviously this V is pointing this direction, okay? So we're raising an elevation this way, and the V is pointing this way, so we're raising an elevation here. So I can look at this map and say, this is the low spot on the road because the V's are pointing up, okay? Inversely, in the ditch here, the V's are pointing this direction. So it means that the low spot's down here somewhere, and this is flowing water down this way, okay? If that makes sense. All right. Understanding contour lines. So this is a video you guys can watch on your own. I'm not going to play it in here, but it is something that you can watch on your own. So now that we know about contours, we're going to take and work on interpolation, so that way you guys know how to tackle that assignment. So through interpolation, there is a small interpolation formula that I threw together here. Okay, so A is the distance between two elevation points. Okay, so let me change my little cursor here to a pen. And so A would be the distance between two elevation points. So let's say I'm going between this one to that one, okay? Well, it says the scale is 100 feet, and like on your assignment, if I scaled this, it would be 100 feet from this X to this X, or from this X to this X. So if we do the old Pythagorean theorem, 100 squared plus 100 squared, this 100 here, and this 100 here between the X's, okay? So it makes our triangle. If we take the old Pythagorean theorem, 100 squared plus 100 squared, it's going to equal our hypotenuse, and that's that distance between these two, okay? So that distance just so happens to be 141.42. Okay, so my distance along there for A is 141.42. B in this formula is the change in elevation between those 2 points. So that change in elevation between these 2 points, actually I picked a bad example here because these are on the same elevation for a contour. So let me erase that and we'll go back a little bit. Eraser. I'm going to leave that bottom part of the formula there because it's going to be relevant. Okay, so let me go back here, grab my pen again, and this time we're going to go from, let's see here, we'll go from this one to that one. Okay, so we have our triangle we're making. Okay, this is the right triangle. This is 100. This is 100. And our hypotenuse is this formula here. So that's A, okay? 141.42. All right, so then we want the change in elevation between, I'm going to change my color here, change in elevation between the 2 points. Okay, so if I take 456.10 and subtract 454.60, that's going to equal, punch that up quick, should be 1.5. You're going to have to punch it up. 1.50. Okay, so that's B. Now C is the distance to the contour line. So typically the contour that represents the whole foot. Okay, so we're trying to figure out where that contour line comes through. So C is the variable we're looking for. So that's what we're looking for. Okay, big old question mark. All right, and let's figure out D then. So D, I'm going to represent with purple. D is the change in elevation from the point to the contour line, or to the actual contour we're trying to find. Okay, so D then, it doesn't matter which one you pick. I tend to pick the lower one. So I'm going to take 454. Actually, I'm going to take the elevation I'm looking for. So I'm trying to find contour 455 in this example, okay? Between here. It'll be 455 and 456, but we'll try finding 455. So 455 is the contour I'm trying to find. Okay, and I'm going to subtract, and I'm going to go for the lower one, from 454.60. Okay, so that difference for D, what we're looking for the formula here, D then is 0.40. Okay, so we have all the variables to be able to solve for this formula here. So let me switch to a different pen type. I'll go with the ink color black. And okay, so A, we figured out, is 141.42. And I'm dividing that by B, 1.5. Okay. We're trying to find C here. So C is there. And then we put in D. 0.40. What does that equal? Punch it out quick. All right, it comes out to be 37.71. Okay, so what I would do then is I'd take my scale and I'd have it at the 10 scale. So you're going to need to have your scale with you. And I'm going to measure between this, and it should, with the 10 scale, it should measure out to be about 141. And I'm going to come out on the 10 scale 37.7 feet. Okay, so it should end up like in here somewhere is where it crosses. Okay, so I make a crossing there. Then I can figure out for the next elevation, I could do this whole same thing again, but this time down here, I'm going to be figuring out what the distance is from 456 from this elevation. Okay, so I'd be plugging in 1.40 here. Okay, that's how much change it is to that one, 1.40. And then I'd get another number, and I would find where it crosses here. So I just make a little line on there. Okay, then I move over, and I figure it out along here, and then I make another line. And then wherever that crosses, you will see, like, you'll be able to draw your contours in. Okay, something similar to that. Now, I'll show you in the next slide how that process works. Okay, so you can see I did my crossing patterns here, and these are all the lines that you're going to have to figure out to interpolate between. Now, some you won't have to, some you will. Okay, so let's take a look at this diagram. So the first thing I'm going to do is I'm going to try figuring out this line in red. Okay, so I'm going to go through and apply that formula, the interpolation formula. And I know that my hypotenuse distance, let me switch to my cursor here. So my hypotenuse distance here, because my scale is 100, and between these x's it's 100, so I figured that out, okay, is 141.42. My change in elevation, which is b, between these 2 points, is 0.9. I'm trying to find c, and to go to the whole contour elevation of 453, I'm moving 0.2 feet from this one, okay, in elevation. So I'm trying to find the distance that I scale that. Well, when I apply it through the formula, I get 31.43. So let's draw that on there. Okay, I'm going to use a red pen. So I'm going to draw that on there. I'm just going to make a dot on the line. So I'm scaling 31.43 feet out. I bust out my scale, and I'm going to say it's going to cross like right in here somewhere. Okay. All right, so that's my crossing point for 453 contour. Okay. So let's check out the next one. So I'm going to figure out the green line now. Okay, so green line, I'm trying to find the 453 contour again. I'll switch to green this time. Okay, so I go through. My hypotenuse distance is that 141.42. The difference in elevation between the 2 points is 1.2 feet. I'm trying to find C, and the difference in elevation from this elevation here to the whole contour I want to go to is 0.1. So I'm moving 0.1 to get to the 453 contour. So I'm trying to find 453. All right, so I go through and do the calculation, and I get 11.79. So that's going to end up like right in here somewhere, okay, when I whip out my scale and I scale it on there and make my dot. Right? So then the next one, the blue line here that we're going to solve for. So I go through, do the same thing again, but this time I'm not using the hypotenuse distance, I'm using the distance between the x's. So that's 100, that's why I have 100 in here. My change in elevation is 0.1, and hold on, there is no contour passing between these two because they're at the same or within the same 1 foot of elevation. Okay, so there's nothing there, so it's 0. We don't have any elevation or a whole contour that we're looking for on this one. Okay, so that's a freebie. There's nothing there. We can't do them, or we don't need to do the math because it's times 0. There's no elevation change. Okay, so let's find the gray one then. All right, so now we're up looking at the gray one here, and we're going to figure out that. Okay, so it's 100 feet again between the 2 points. It's 0.4 feet of elevation change between the two. Okay, this time we're trying to find the elevation at 454 because that's the elevation that ends up between these two. Okay, so in order to get to 454 from the lower one, I have to go up 0.3 feet in elevation. So I apply that, and I find out I have to scale 75 feet on the scale. So if I change my color to gray, I'll just do it as black because I don't have gray. I'm at 75 feet away from this one if I scale with a 10 scale. Okay, so that's the 454 contour there. All right, so let's figure out the next one. We're going to figure out purple, the purple line. Okay, so the purple line, we change elevation between the two. I'm going to change my ink color to purple. All right, so the purple line, it looks like we have the 453 contour that's ending up between these two. So It's 100 feet between them. That's A. B is the change in elevation between the 2 points. C is what we're trying to find. And D is the elevation from my lowest elevation to the point I'm trying to find. Okay? It just so happens it comes out, the math works out that C is 1250 elevation, okay, or 1250 distance. So 12.50 feet, it's about right here, okay? So that's that. That's for the 453 contour. Let's figure out the brown line now. So we have to figure out where that contour crosses the brown line. All right, so we're trying to find the 453 contour again. We used 100 because that's the distance from this point to this point. For A, and for B, we use 1.3. That's the difference in elevation between these 2 points. C we're trying to find, and D is the distance or in elevation change to that contour, the 453 contour. So we do the math. We come up with that we have to scale 15.38. So I scale out 15.38, and I make my mark with the wrong color. Let's erase that. Okay, let's put the right color in there. Well, there's not a brown. I'll do orange. Okay, so I put my mark in there at 15 feet. This is a little ways away from 15 feet, but close enough. You guys get the gist of things. All right, so let's figure out the next one. It just so happens that there's 2 moments of or 2 contours that cross between those 2 elevations. So we have to figure out the next one, okay? This time I'm going to change the color for this one, so that way it's a little bit different than the last one. I'm going to go yellow. I know yellow's hard to see, but we'll roll with it. So it's even hard for me to see where it's at. Okay, there we are. So we have 100, which is the difference between the 2 stations. The one is for the horizontal distance between the 2 stations. The elevation change between those 2 elevation stations is 1.3, just like the previous problem. But this time we're moving 1.2 feet in elevation change from the lowest elevation. We're trying to find 454. So I'm going to, there's 92 feet, so I'm going to say we're right here, okay? A big yellow dot is where it crosses. Okay, oh, let's go back. So I have all this in there. So now I'm going to take and trace in my elevations, okay? So these all happened, the purple, the green, the red, and the orange all happened at the 453 elevation. So I'm going to connect the dots, okay? So that's the 453 elevation. If I connect these dots, this is the 454 elevation contour. So I just drew in this contour is my 453 contour. This contour is 454. If I kept going this and we started drawing this in, this contour would probably do something like this, okay, for the 454 contour. And then I would pick up the 455 contour, and it's going to be something like this. Okay, so that'd be like the 455 contour. So you're gonna have to do this to make crosses all the way across that whole sheet of paper and draw these all in. So I'd be cautious when you do the assignment to sketch. If you do these lines in there, just for so that way you can figure out where you're putting your point, draw them in really light, because when you go to do the contours, if these lines are dark, the crossing lines are dark, your contours you won't be able to see really well, okay? So this is how you'll have to figure out your contour lines, your moments of elevation. So like I said, this is the 454 elevation. You're going to have to label your contours, and you always label it on the contour. So this is 453. This one here, if I did the interpolation, I could figure out that this one was 455. Okay, so that's how that works. Let me close out of the PowerPoint now that I did all that. Okay. All right, back to the assignment then.